Okay, so I'm Glenn Cunningham. I'm a longtime professor at Tennessee Tech in mechanical engineering. I have a pretty extensive background in industrial energy efficiency. We have a, U.S. Department of Energy funded uh, grant with DOE, the Industrial Assessment Center. We're in our 15th year. We offer no cost to industry complete energy assessments of facilities. It's targeted towards medium and smaller universities, but the program is pretty flexible. So if you have an interest in that, please let us know. Um, and so with that, I don't know, John Smigel, are you on? If you're on, you might want to say a few words about the program to folks. John's our director out of DC. He may not be on this one. He's been on the other calls. Okay, so I'll go ahead and get started here. Hopefully.
And Glenn, I think we were going to reserve a little bit of time at the end for questions, so we'll ask the participants if they have any questions to hold them toward the end. And in conclusion, I will review TVA's current incentives as it relates to UVGI, and we'll cover that along with the flyer that was distributed to everyone at about maybe 15 minutes before the conclusion of the workshop. Thank you.
Yeah, I'm not sure this one's going to run quite as long as the first two, but we'll see. We certainly won't run over. Okay, so we're going to look at mostly centrifugal fans, and this is a breakdown of kind of an expansion of a typical centrifugal fan. You see, we've got some different areas here. We've got a blast area. We've got a cutoff down here. We've got a discharge area, outlet area. When you get into some design type calculations, the ratio of these areas becomes a factor that has to be considered. We have, our scroll casing that the wheel fits into. This is the impeller of the wheel that spins around. Air comes in here and comes out 90 degrees. I'm sure y'all are probably familiar with this. There's different styles of blades that we'll discuss just briefly here shortly for different types of applications. We have an inlet supporting collar, and we can put what we call inlet guide vanes is one method of capacity control that can be strapped on this inlet that we'll see here, I think in the next slide. Okay, and so just a couple of pictures of typical centrifugal fans. Nothing really special about these. They're often belt driven. They don't have to be belt driven. They can be direct drive to the motor, in which case then you may have discharge dampers or something for capacity control. We're going to be really concerned about capacity control because that's where a lot of inefficiency can work its way into the system. And we'll talk a little bit about different types of belts towards the end of the presentation. We have standard V's, notch V's, synchronous belts, and all that. And there are some fairly small but energy savings associated with perhaps upgrading your drive system. We'll mention that as well. On the right over here, we show the variable inlet vanes, or what I call inlet guide vanes, different terms for the same thing. These little kind of pie-shaped dampers that rotate open and closed. And it's interesting, these control capacity by imparting the pre-rotation to the air as it goes in. And so these are set up to, the more you close them, the more pre-rotation, because the air gets pulled through these things in a swirling pattern and goes in, and it's swirling in the same direction that the wheel is turning. And so the more you pre-swirl it, the less effect the wheel has on the capacity. And so you can adjust capacity by adjusting the amount of swirl coming in. That's not just resistance. I mean, there is some resistance, frictional resistance across the blades, But that's a completely different approach as, say, a discharge damper or a throttling damper that could be right on the discharge of the fan. It could be on the suction of the fan too, or it could be out in the ductwork. And so we'll talk a lot about that. So you typically see these things, there'll be some sort of control linkage, and it goes back to the control system that says, hey, you're blowing too much air, you're not blowing enough air. We adjust the inlet guide vanes and we adjust the capacity or the amount of air that's being blown by the fan. Okay, this is shown for centrifugal fans. The different types of impeller designs that are out there, and they all have different characteristics. You get different pressure flow capabilities based on the impeller type, and certainly different efficiencies. I think the most efficient type out there is this airfoil fan, or airfoil blade design on the wheel. They kind of lay backward incline, and this is an airfoil shape on the individual blades. These very good efficiency typically. They can't move particulates. There's a lot of dust loading, or if you're trying to move product, or you just have a dirty airstream, these can erode, and so not recommended, only recommended for clean flows, but very high efficiency. And you can step down to these backward inclined blades. They are very good. They're also very efficient. If you have more dust loading, more material moving, high pressure applications, we typically get into the radial or radial tip. A lot of smaller HVAC fans are forward curved, etc. And then you see comments over here about the scroll design, etc. This, I think I stole this from ASHRAE. So that's the source of this particular figure. There are plenum fans, plug fans, more HVAC type applications. On an axial type fan, so the fan would fit into the ductwork. So you would typically probably have round ductwork, and this fan has a round casing on it, and it bolts right into the ductwork, and it's kind of like a propeller type fan. And you have these things, the more sophisticated ones, the better ones, the higher pressure ones are variable pitch. Like in the old days, I used to fly a little bit, and the better, more sophisticated small planes have variable pitch props on them, so you can change the pitch of the blade. And that's actually a very efficient way to change capacity on a fan. So, the tech, and we'll see all these technologies listed in a second, but a lot of times we look at going to variable frequency drives to do variable speed control, and you can certainly do that, and you can do that on a centrifugal and an axial fan, or on these axial fans, you can go to variable pitch control. Now, in the efficiency of the two, or the VFD and the variable pitch, is pretty close. I've heard stories about maintenance issues on the variable pitch. I don't really have any direct experience with that because I've not seen all that many of these. I know some of the power plants on their really larger fans have gone to variable pitch blades on the fans. And one reason is because those fans are so large, and if you're at medium voltage, the VFDs become more expensive, and they require cooling because of heat generation in the drive. And so the VFD at medium 2000, above about 600 volts, becomes a much larger investment. So if you're a power plant, or you're dealing with really large fans and you're going to replace one, put a new one in, you can get that same efficiency on turn down with these variable pitch axial fans as you can the VFD. So that's something to consider. Just some pictures. They're tube axial, vane axial fans. This would be a variable pitch prop over here on this one. This would be a fixed pitch. And another option here on the axial is the motor can be outside of the airstream, or the motor can be inside the airstream. So, it could be, if this is a cooling flow, that's a good clean, airflow or something, it could cool the motor and increase motor life, and make it a very good environment for the motor. Or if it's a dirty, nasty environment, you wouldn't want it in the flow. So it just depends on what you're doing with that. Just kind of, this is the ASHRAE screen capture on the different axial fans. I guess the low cost cheap one is just, they call it propeller fan. This would be for like exhaust applications. You see them in plants all the time up on the walls where they're going to exhaust or blow air in or out of the plant. They usually don't have very good efficiency. They can't generate much pressure, but they will move a lot of air. And then the tube axial and the vane axial here, you know, have more pressure capabilities and have better efficiencies. Okay, I think I used this slide in the pumping presentation as well, but it just has to do with if you have a large plant or maybe across a corporate situation where they have a bunch of plants, how do you figure out which fan systems you're really going to look at? And it's just a screening slide. Basically, you can start all fan systems, all motor systems, whatever. And, you know, seldom use small loads. Don't worry about them so much. Big loads run a lot, but you may have, if it's non-centrifugal, it's not going to have the good energy reduction capabilities with speed. So that you may want to put that off. Or if you already have speed control, then you may have already done the project. So that puts us over here with big centrifugal loads that run a lot, that have some sort of a symptom that would indicate that we have some energy saving opportunities. And that symptom is probably going to be pinch dampers, either discharge or inlet guide vanes. So if you already have VFD speed control, then you're probably already done the project. Some comments about what leads to these opportunities. Well, we all pretty well know that the design procedure is very conservative, you know, because, you know, if you're a designer and you may have been in this situation, you have to select a fan somebody's going to go out and buy and put in to move a certain amount of airflow through a particular system. Well, you're going to be very, very careful that that fan is big enough. You know, if it's a little too big, no harm, no foul. If it's too small, then everybody's got a problem. And so from the design engineer, he's going to be conservative. He's going to make sure that he estimates enough pressure drop. The contractors, when they go to purchase that thing, they say, well, you know, he called this one, I'm going to go up a little bit. I'm going to put this one's a little bit bigger. I'm going to put this one in, etc. Oftentimes when you turn the thing on, holy moly, we're looking for 10,000 CFM and we've got 17. Well, no problem. We'll just pinch the dampers. Okay, and that works. That reduces. You got your 10,000 CFM. Everything runs. Everybody's happy, except the guy paying the utility bill. He's not so happy. It may take him a little while to figure it out, but he's not going to be terribly happy with that. So because it's going to be probably a pretty inefficient operation. Sometimes we just run things when we don't need to, turn them off. And, you know, we've got really two ways. If we have an oversized fan and we're looking at pinch dampers or inlet guide vanes, you know, we can go the variable frequency route, or if we're on a pulley situation and we don't ever change the position of the dampers, well, we can just do a shift change and, you know, get with the fan manufacturer, take some measurements, figure out, you know, maybe we're at 750 RPM, we could go to 600 RPM, and we could then open the damper and we would get the same flow. The system would never know, except the energy use on the motor would drop significantly. So, you know, it depends whether we're going to have to modulate this flow. If we are, then we can't just do the shift change. We may be looking at a VFD or, you know, on an axial fan, a variable pitch prop would do it as well. Okay, so a lot of this presentation is going to pound in on these different control methods. So this is a figure that comes from Department of Energy literature. It shows a bunch of different control mechanisms for fans. And so the ones that we typically see over here, we'll see they call this outlet vanes. I typically call them discharge dampers, but this is all frictional. usually dampers pretty close to the blast in the ductwork right downstream of the fan. And we can see as we reduce airflow from 100 down towards 20%, the power falls, but it sure doesn't fall a lot. You know, it's pretty, frankly, it's pretty crappy. And this shows an increase above 100%. And that's because of the frictional loss across the damper when the damper's wide open, compared to some of these other technologies, which wouldn't have that component in the system. So that's why this goes up, you know, well over 100% at 100% flow. Disk throttle, that's something you don't see. I'm not really going to talk about that. Here's our inlet guide vanes. And, you know, it shows this curve in the upper load range is pretty good. And so one possibility we'll see is if your fan is going to spend a bunch of time up here and you're doing it with discharge dampers, you can retrofit most likely to inlet guide vanes, which is pretty cheap on a big fan compared to a variable frequency drive. So now if you're down here in the lower load ranges, we start to see that the speed control, the VFD down here is significantly better. So if you're down, you know, 40, 50, up to 60%, we've got significant savings in going on to the VFD, which may well justify that investment. And you see the controllable pitch blades on the axial fan hangs in there really close with the VFD. So that's pretty good. And the fan law, this is the fan affinity laws, which is kind of theoretical stuff, which you can't really achieve in, you know, in any sort of an actual situation, but it just gives a comparison. Okay, so I've got one equation. You know how engineering profs love equations. So this one's not too bad. I'm not going to pound you with a bunch of fluid mechanics equations here. But so the fluid, the fan fluid power, or the amount, the energy in a flowing airstream you can calculate as flow rate, CFM, times pressure, inches of water. And if the pressure is high enough, you got a compressibility factor. Usually this is 0.98, 0.99. So most of the time it's not a big deal in typical fan situations, but if the pressure is high enough, it can be. And then these are some constants that convert all this into horsepower. And I'm calling this air horsepower. Doesn't have to be air. It can be whatever fluid you're flowing through the fan. So that's what the energy that's actually in the airstream. You can think about this. Say if you went across a damper, maybe you drop 10 inches of water across a damper. Well, you can put 10 inches in here, and this will tell you how much energy you actually dropped out of the airflow as a result of going across that damper. Or it could be going across a fan and you get an increase, whatever. But this is energy in the fluid. Well, now, you know, energy over time, I'm sorry, that's power. So power over time is energy. Okay. And then if you want to get to input energy, you got to start dividing by efficiencies, because that fan might be 70, 75% efficient. So then if you want to get the brake horsepower into the fan, you got to divide by the fan efficiency. Well, then you may have a drive efficiency. So you may have a belt drive, which is 96% efficient. So you got to divide by 96% to put the inefficiency of the belt in it. And then the motor is 92% efficient. So you got to divide by 0.92 to get the efficiency of that. And then, you know, if you have a VFD or something, there's inefficiency in that. So you can back up to the point that you can calculate the power required to put into the motor in order to make all of this happen, or into the drive. Okay, well, but we notice here that if we want to reduce energy, what do we have? We don't have really all that much to work with. We can change operating time, turn it off if you don't need it. You can change the amount of pressure that you generate across a fan, or that you drop out across a damper, or you have inefficient ductwork, and maybe you've got an extra 5 inches drop because you got 3 turns that you don't really need, but there was something else in the way and that's the way it got installed. Or you can reduce flow rate. So those are really the variables that we have to work with. Okay, so the fan curve, this is all the information that is typically provided on a fan curve from a manufacturer. Now, we'll have different scales. So, we'll have a pressure scale, we'll have a power scale, which may actually be on the right. We may have an efficiency scale. There may be a double scale on the right, whatever. So we'll have different scales on this stuff. But we've got airflow volume on the bottom, CFM, could be in hundreds, could be in thousands, depends on the size. So just starting at the bottom, we've got the fan velocity pressure. So that's the portion of the total pressure that is caused by the velocity of the air molecules as they move through the duct. And we see, if there's no velocity, if there's no flow, there's no velocity, there's no velocity pressure, and it goes up basically as kind of a squared relationship. Then let's see, let's go to static pressure. So this is the static pressure generated by the fan based on measurements by the fan company, the manufacturer. And then if we add the velocity pressure and static pressure together, we get total pressure. So you can plot this curve. And it is the fan static, I don't know if I said that moves the air through the duct. So a lot of times designers are really concerned with this fan static pressure curve for selecting a fan. This would be a recommended operating range for this particular fan in terms of fan total pressure. So the pressures would all be on the same pressure axis. And then we have the fan power. And you see, based on wheel design, lots of different shapes of these fan power curves. You see this thing, as it goes out in volume flow, it tends to, because the pressure is falling so rapidly out here at the end, that the power tends to drop off a little bit. And so sometimes this goes up. It just depends on the shape of the curves. But so that would be probably on a scale over here on this axis. And then we have fan efficiency. And we can see the suggested operating range is towards the peak efficiency. And usually you don't want to get too far to the right, because sometimes it depends on the wheel design. You can have areas of instability over here at low enough volume flows where the manufacturer really doesn't want you to operate, because you can get vibrations and resonances and issues. So you typically want to stay out here on the right-hand side of the curve, not over here to the left at lower volumes. Okay, that pretty well says that. Okay, just to kind of beat home this total pressure, static, and velocity pressure. So static pressure is the bursting pressure on the duct. It's the forces that say operate trying to push this duct apart. Velocity pressure is the impact pressure that you're going to feel, like when you stick your hand out of the car, you're driving 60 miles an hour, you can feel the impact of those molecules. Now, the air is not moving, but you are relative to the air, so it's the same thing. And then, so total pressure is the sum of that velocity pressure and static pressure. So if we want to measure some of these, say we have air flowing through a ductwork here, if we just drill a hole in the side of the duct perpendicular to the flow, and we're assuming here that this flow is all in the axial direction, and if it's turbulent enough, well, we may get some impact into the static port, but anyway, that's just the way it goes. So the static pressure then would enter this portion of this U-tube or this manometer, and we would turn it up, and so the end of it is open to atmospheric pressure just in the room beside the duct. And so then, we got more pressure trying to burst this duct. And so it pushes the manometer fluid down relative to this. And so we measure this height difference between these two meniscus. And we can then, knowing the density of this fluid, we can calculate exactly, very easily, what this static pressure is at the duct at that point. Okay. We go to the middle tube, and these last two are called impact tubes. And so because this is total pressure coming in here, because we still have static all throughout the interior of the duct, but now the impact, the kinetic energy of all those molecules is banging into the end of this tube, and those will measure the velocity pressure as well as the static pressure. So this would be a total pressure tube. So we get total pressure in here. Again, if we open it up to atmosphere, then the distance between this meniscus and this meniscus indicates the total pressure in the duct. So here I'm measuring static, here I'm measuring total. If I subtract the two, I'm going to get velocity pressure, but I don't really need two tubes. I can do that with one tube if I just set it up like this tube on the right. So I have a total pressure or an impact tube open to the flow in the direction of the flow. So I get total pressure in here. I connect the back portion of the tube to a static pressure port just drilled in the side of the duct. So I get static pressure pushing down here. So I do the subtraction as part of the measurement. And so the difference in elevation from this meniscus to this meniscus directly measures velocity pressure, which then I can easily calculate velocity at that point in the duct. Okay. So that may be a little more fundamentals than you wanted, but what the heck, you got it anyway. So a Pitot tube is a standard device for measuring airflow in ducts. And so this shows a Pitot tube. And so a Pitot tube is basically a tube within a tube. So the inner tube is the impact tube, the total pressure. So it's just completely open and comes down, and we've got a manometer connection down here on the bottom coming out of it. And then there's a concentric tube around the outside, and it doesn't get any of the impact pressure. It's simply open on the sides. And so these are static pressure openings, and there's, you got 8 holes, and there's some specs on it here and all this sort of thing. But anyway, we allow the static pressure in the outer portion of this region. And so the other side of the manometer hooks in here. And so this then shows static pressure, total pressure, and the difference being velocity pressure. So that's how a Pitot tube works. Okay. This is the calculation. This slide, instead of total pressure, calls it stagnation pressure, static, and dynamic or velocity pressure. A few different words, but it means the same stuff. So here's an equation for total pressure is the static plus rho average velocity squared over 2. And so this is just density, which if you know the fluid, you ought to be able to find the density for it at that location. So we just solve this equation for a velocity, and bingo, it's pretty simple. The PT minus PS is just velocity pressure, 2 and density square root, bingo, and you got your velocity. So pretty simple. Now, if you're going to get, if you want to get the most accurate flow measurements, you need to do traverses. And this shows for a round duct, it's really recommended that you do a horizontal and vertical traverse because of, this is most likely going to be turbulent flow, and there's no telling what the distribution is really going to look like at the plane that you decide to take these measurements. You want to get downstream where all this is kind of calmed out and you've got a fairly predictable velocity profile, but I mean, it's tough finding the perfect spot out there in a plant. Okay, and so what these different rings recommend equal concentric areas. And so if you respect these different radial spacings, then you can take these pressures and you can just average them all together because they represent the same flow area as you come across the cross section of the duct. That's how these different fractions of radiuses are calculated. So that then if it all represents the same area, then you just add them all together and you take an arithmetic average. If you just jump around, then you're not going to get as accurate a result. Now, if you have a rectangular duct, it's easy. You just divide it into a grid and you say, okay, I'm going to take 12 measurements, and you try to get in the center of each of these little boxes to indicate that they're the same area. So equal areas. So there you go. Okay, so let's look at a little system. So where does a system operate? At the intersection of the system curve and the fan curve. Well, the fan curve we know supplied by the manufacturer. And the system curve is really is calculated by the designer. Or if you go out to a fan in the field, you can measure a flow and measure a pressure, and that's where you're operating. So then and if you go through 0, 0, which most fan systems do, then you got 2 points. If you got 2 points, you can draw this curve. So that's kind of where we're going. But the system curve represents the required pressure to push a given flow rate through the duct system, everything but the fan. And of course, this is the fan curve is the capability of the fan. So where those two items come together is where you're going to operate. So this slide is going to drill down a little bit on system curves. What is a system curve? I think I pretty well described that. Sometimes I jump ahead here a little bit. But system curve shows how much pressure is needed to move different flow rates through the duct system, basically. Okay, so here's an equation. Total head can be a static head plus just a constant we're calling K prime times the flow rate CFM squared. Okay, now if, for example, you had a fan that was blowing into a pressurized chamber, that pressurized chamber might be at 10 or 15 inches of water. So that discharge pressure represents a static pressure that has, this is a frictional component over here. That discharge pressure that you have to force that air into has nothing to do with the friction through the ductwork. Okay, so if you do have to discharge into an area that is of elevated pressure, then that becomes a static head that has to be added in here. Most fan systems don't do this. So we typically show the fan curves going at 0 flow through 0 required head, but not all systems. Or if you were pulling air out of a pressurized region, then that could provide a negative static head because that would help move the airflow through the duct. So there are some exceptions to this, but generally speaking, this is the equation of the system curve that we're going to be working with. Okay, we'll get back to that more in a minute. Let's look at fan affinity laws. And you may say, oh my gosh, look at this mess. And it does look a little bit daunting at first blush, but it's really not too bad because we figure most of the time we're using affinity laws. We use these to redraw fan curves. That's really the correct use of the affinity laws, to recast a fan curve for a different wheel diameter or a different rotational speed, or perhaps a different density if we change the density of the fluid. So that's being blown, the air or whatever gas it is. But generally speaking, we're changing speed. So this is the diameter of the wheel. If the diameter of the wheel is not going to change, d corrected over d cubed is 1. So we get to ignore it. This is compressibility factor. If we're not really changing the pressures or anything much, then the ratio of compressibility factors is not going to change. So most of the time this drops out, or it's a pretty minor player. So then we would wind up with the new speed divided by the old speed times the old flow rate is equal to the new flow rate. So in other words, if let's just take an extreme example, say we doubled the speed of the fan by a factor of 2. Well, then we're going to double the flow rate because it's linear with that ratio. So double the flow, double the speed, double the flow. What happens to pressure? Say the wheel, this is out because we're not changing the wheel. We're not changing the fluid, so the density ratio is the same. We're not changing compressibility factors much, so we're going to drop that. So it's just a speed ratio, which I said was 2. If we're going to double it, 2 squared is 4. So whatever pressure we had before, it's going to be 4 times that. And that would apply to total pressure, velocity pressure, and we would subtract the 2, so it would apply to static pressure as well. So you see on power, H is power. So again, the D's drop out, the rho's drop out, and the K's drop out. So if the speed ratio is 2, when I cube it, 2 times 2 is 4 times 2 is 8. So now that power is going to be 8 times what it was previously. And then these are just definitions of efficiencies based on that initial equation that I had up there. Okay. Now, if you do change wheel diameters, you would probably have to buy a new one. Then you can, and if you turn it at the same speed, then you can go back and recast fan curves for different wheel diameters. But I don't see that come up very often. If it's that bad, you're probably just going to replace a fan if it's that bad. Okay, so this is an example, just runs through a little simple calculation. Where we had initially a fan turning at 600 RPM. That's this curve. And I've got a couple of system curves on here. This relaxed system curve might be a curve with a damper open. And then this might be a curve with a damper closed. I don't know. I can't remember where I got this from right now, so I'm not sure, but that's kind of what it looks like. But at any rate, I'm just in this calculation, I'm just working with this D point over here. So if you look at the initial flow rate was 6,000 CFM, and the pressure is about 1.13 inches of water column. And so then if I speed it up to 650, well, where's this point going to be on the 650 RPM curve? Well, I can calculate that point. So I just take the speed ratio of 650 over 600 times the 6,000. And it says, okay, that point is going to move to 6,500 CFM. And the pressure is going to go to the speed ratio squared times the initial pressure, 1.33 inches of water column. So those are the conditions at point E. Okay, so just want to show how to use those affinity laws. And that's what they're really intended for, is to be able to recast the fan curves to different RPM. Then you look and see what your system resistance curve is, and you see where your operations, how your point of operation is going to change. This shows density effects. And so, you know, I don't know that this comes into play very much, but so for example, if we heat it up, all of a sudden we were blowing cold air and we're going to blow really hot air, you know, how would that affect the operation of the fan? So we see that the flow rate, the CFM is not going to change, but all of these other total pressure, static pressure, and velocity pressure are going to change by the ratio of the new density to the old density, okay, as well as the fan power. So as the density of the fluid changes, it does have an impact on the fan. This shows an example of it. Let's see, this is for the example, we've got 800 RPM. We started at standard conditions, 70, oh my, and we jerked it, we raised it to 600. Now that's a pretty extreme change in temperature, but that was done in order to get the density to fall to half of what it was before. So I'm not saying this is terribly practical, but nonetheless, it's certainly not impossible. So you can see, just when you go through the equations, the standard density fan curve is up here, and it's going to get cut in half as far as the pressure, because the density is half of what it was before. And the initial brake horsepower curve is up here, but because this air we're pushing only weighs half as much, it takes roughly half, it takes half the power. And so we get a different brake horsepower curve, which is half of the original. So I just kind of, and notice we do have an equation here for sound power. So you can calculate a change in sound power generated by the fan as well. Okay, a little bit on motor performance characteristics. This is for a 200 horsepower 4-pole motor, synchronous speed 1800, full load operating speed 1785. And we can see as we unload the motor, we get a pretty linear increase in speed up to the unload point. 200 horse at 40 horse, what is that, 20%, down to 20%. Efficiency is pretty flat. We lose a little bit in motor efficiency, but not much. Power factor falls off more significantly at 40 horse, which is 20%. I'm down about 55% on power factor, which could be an issue if you got a lot of that going on in your plant. And we see how the current falls as a function of load on that. So just kind of general stuff that's in the background. Motor efficiencies from NEMA premium efficiency down to standard efficiency. You can see just kind of as a reference. Okay, variable speed drives. This is some data from Oak Ridge. 50 horse, two poles, 3,600 RPM synchronous. We're 98% at full load, which would be up here off the curve. When I put the drive on there, it's going to lose 2, 3, 4%, something like that, depending on the drive. And so that's just a factor you have to consider is the drive efficiency as well. Other ways to make motors variable speed, this is be a magnet drive, a magnetic coupling type slip type drive, not as efficient as a VFD. And so you see the VFD, the overall electrical power falls more, but still, even with a magnet drive, it still comes down pretty significantly as we reduce speed. Okay, so these are the different fan, centrifugal fan control technologies that you typically run into. So you got your inlet guide vane control up here as the first one, and we're talking pre-swirl. We talked about that. It's a pre-swirl thing. It's not really a frictional thing so much. Then we have inlet damper control. So you can have these engineered inlet boxes with dampers on them. And they also induce a swirling effect. They probably have more friction than the straight inlet guide vane. So they may not be quite as efficient, but they can be pretty good. So for a big fan especially, you can buy an engineered box and you have to work with the manufacturer to see how efficient they've tested that to be. The bad one is the outlet damper or discharge damper. This is all frictional stuff. And so this is the one we want to avoid. You can have an adjustable gear control or a slip coupling or something like that. They're not typically as, the gears certainly are not as good as the VFDs. And then of course you got the VFD control. This just looks at some of the different configurations. So for the discharge dampers, lots of different configurations. So, and performance is going to vary depending on which damper and how the ductwork is put together at the discharge of the fan. There's a factor called a system effect factor that you can get into to try to evaluate some of that. But, you know, you can have opposed blade dampers are pretty good because they shoot the air straight into the ductwork. If you have these parallel blade horizontal, then they're going to throw all the air down to the bottom of the duct, and it's going to swirl around as it tries to eventually establish a decent velocity profile. And then you can put the, instead of horizontal, you can put these vertically. So it depends what you have as to really the performance characteristics. Your inlet guide vanes are going to strap on this cone, which go directly into the fan. This shows the inlet box with the different dampers. They can either be parallel or opposed blade. Depends on how this box has been engineered to get the pre-swirl to adjust the capacity. Some pictures. These are pretty nice. So this shows what the inlet guide vanes look like out there in the field. You know, we got, you know, belt drive on this thing, nice little caves. Looks like we got 4, I think that's 4 belts on it. And these things are pretty much opened up, so you're not getting a lot of pre-rotation. This looks at it from the other angle. The more these things tilt over to the side, the more that air starts spinning before it hits the wheel. Uh-oh. Oh, I may have messed up now. Just a second. I think I'm going to have to stop sharing. Screwed up the PowerPoint. Just a second. Where's PowerPoint? You always got to have a hitching to get along somewhere, don't you? Let's try this. There we go. Okay. I've been changing slides by clicking, and sometimes it blows up the figure. Okay, so this is kind of, again, a similar, probably a better curve than that one I had from DOE. And it shows we've got nominal flow, percent flow versus required power. So it's similar. And so it shows all of these different options that we just talked through. And of course, the outlet damper is the worst. And then the inlet damper, which is still doing the pre-rotation, they show, this is from ABB, I think is where I got these. They show it not being quite as good. I think it depends on the inlet box and how well it's engineered as to whether it's this much worse than the, I'm sorry, all right, well, this is the inlet guide vanes. And so they're showing the difference here. So the outlet damper is bad. The inlet damper is going to be better. Whether it approaches the inlet guide vanes depends on the engineering. And then of course I've got the adjustable gear, which is still adjustable speed. So it's pretty good, but it's not as good as the variable frequency drive. So that's kind of what that's about. Okay, and so again, if I pick my 60% here just to kind of pound home. So if I'm doing it with discharge dampers, I'm what, 78, 79% required power. I'm doing it with inlet guide vanes, I'm down here, 48, 49%. And if I'm doing it with variable speed drive, I'm down here at what, 24, 25%, something like that. Big improvement. Okay, this is some data from NREL, National Renewable Energy Lab. They published a study several years ago where they took a bunch of data on some fans. It was at a particular building. I think it was in Colorado or someplace, but they did a detailed study. And so this is actual measured data on, it's like a 20, 30 horsepower motor, something like that. It wasn't a huge motor, but kind of medium size, where they tested the different control options. And so these are the discharge dampers. This is the inlet guide vanes, and this is the variable speed drive. And then I went ahead and put this in Excel and fit curves to it. So I've got, this nice little curve for each one of these. And so if I know the percent full load flow, then I can use these curves to calculate the percent full load power, the change in power. And so you can use that to estimate what energy savings could be. Now, okay, let me go back. Notice this is percent full load flow. Well, when I go out there in the field, and I got a bunch of pictures here coming, maybe I should have put them before this curve, but what I observe, unless I take measurements, is a damper position. So how does damper position relate to percent flow? Well, so this is, and I've got my heading up here, and I really don't know how to get rid of this thing. So you can't see, but the heading on the slide, this is for discharge dampers. Okay. Now, it depends on the configuration of the damper, opposed blade, parallel blade, horizontal, vertical, how the ductwork's connected. So you can get a lot of different curves. So this is presented as a typical curve, not that this is going to fit any one particular application, perfectly. But for example, you need to note this. If I observe a 50% damper position, well, I'm likely to be 70% flow, because these things are not linear at all. If I'm at 70% damper position, I'm over here, I'm like 88, 89% flow. And when I go to my power curves, it's percent flow that I'm going to correlate to power. So I have to be concerned with this. And here's a curve that I generated based on some data on inlet guide vanes. Is this perfect for all inlet guide vanes? No, I'm sure it's not. But is it representative? I certainly hope so. You know, I must say it's easier to find damper data than it is inlet guide vane data. I've had much more trouble finding this type of data than the other. ASHRAE has done significant studies on discharge dampers, and there's a bunch of data out there through ASHRAE you can get your hands on, but not necessarily inlet guide vanes. Okay, so this is, now I've got some pictures and some analysis that I did. So this is out there in the field. I have no idea. One of my mini trips, climb up on the roof. You know, this is on the blast. This is blowing air. This is probably on a dust collector or something. Run into a lot of dust collectors in some of the companies that I visit. And so those are discharge dampers. And you walk up to it and you look at that little handle and you go, I wonder what percent open that is. And, you know, you start looking, it's real nice if somebody would write on there, on one end it's open and the other end it's closed. Sometimes they do, a lot of times they don't. You can put a power meter on the motor, and if they'll let you move that damper position from one extreme to the other, if you basically shut it off, the power is most likely going to fall. And so you can figure out by looking at the power meter on the motor which way is open, which way is closed. It's hard to have confidence. If you can look, if you can work with the people that work at the plant, somebody there probably knows. But at any rate, this is the kind of thing, if you're doing a quick walkthrough and trying to, you know, like a treasure hunt kind of thing or a short-term energy assessment, that damper position is maybe all you have to work with. And you can probably take electrical power measurements on the motor to see what it's pulling. Okay, well, here's this colored thing from Excel is from an Excel sheet that I put together that will do the analysis based on those curve fits. So I put those curve fits in there, and then, so now I only have to put in, you know, the basic input information, and it'll calculate savings for me. So I read that damper to be 70% open. Now, somebody out there might want to argue with me, and that's fine. You know, your number may be better than my number, but anyway, you can't run the analysis until you make an estimation. Now, could that be, it could be 30, 35% open, but you know, I don't know. But anyway, just for this example, I estimated this at 70% open. It was locked down, and lockdown would indicate that maybe they don't change it very frequently, but you can tell they have changed it by the way the paint's been scraped off and this, that, and the other. It looked like it may have been up here initially and got painted there, because you can see how the paint chips, and then when they pulled it down, it broke the paint loose. So maybe this was more throttled, or maybe this was more open, you know, I don't know. It was a 125 horsepower motor. It was estimated at 96.3 kW at the 100%. If we opened it up completely, that was the estimate, which is loading a 125 horse motor pretty significantly. So if you look at the inputs over here in the Excel sheet, so first of all, estimated VFD cost. So $100 a horsepower to purchase, and I got $50 a horsepower to install. If we could do this with a shift change, I'm estimating this at $1,500 for new shifts and belts. The electrical energy cost 5 cents a kilowatt hour, and the demand cost $15 a kW. And, you know, asking how many months do we want to calculate demand savings, because, you know, it's possible this could be only run 6 months a year or something, but in this case, I got 12 months. Hours of operation, 8,000 per year. So this is where you input the full load. Like if you open the damper to 100%, that's our 96.3 kW, because that refers to the 100% power number right here. Okay, so that's why you have to have that. Damper position, 70% estimated. And so then when I go to my equation, so this is for discharge dampers. So you see at 70%, I'm about 88 or 89% full load flow. So That's what comes back from that curve fit, 88.82% flow. And so the discharge damper power then at this flow would be estimated to be 93.66 kW. Now, that could be a measured number if you measured it. And so then you could adjust this number to give you the measured number there. That would be fine as well. If you were doing this with VFD control, we would be at 68.75 kW. So the difference there is our power savings. And so the demand savings comes out a little short of $4,500 a year. Energy, not quite $10,000 a year. So we're pushing 15,000. Energy savings, 199,000 kilowatt hours, 299 kW. It's 125 horse motor. And so the drive purchase and installation is 18,750. So if we did this with a VFD, it's a 1.3 year payback. If I could do it with a shift change, and I'm willing to just live with that flow, I could do it with a 1/10 of a year payback. That's pretty good. Invest what, 1,500 and save 15,000. Whoa, that's just not too bad, is it? No, it's not. That's pretty good. So, you know, it just depends. Okay, there's another one, a little Kais blower you see out there. And, you know, really the big question is, what's the damper position? So, you know, I would expect if this handle was perpendicular going straight down, that damper would be shut. That's a common way, unless you have some other indication of interpreting this. And if this handle was parallel with the duct, so if it was raised up here, then it would be 100% open. Now, you do have a slip coupling here, so if you can shut this thing down, or if nobody knows, you could take those screws off and probably get in there and look at this one pretty easy. So that would be a possibility. But anyway, to do this one, I said that's 35% open. You know, you can argue with me, feel free. I was 20 horse motor, 15.6 kW at 100% flow, and then go through the same type stuff over here, just changing the number. So there's probably not a lot of point in going through bludgeoning our way all the way through. You can look through the VFD cost. It's small, 20 horse motors, 3,500. So that gets us about 6/10 of a year payback. Shift change, I estimated this one at $1,200, which would be a little over 0.2 years. So could be a good project. This is inlet guide vanes. And so then this, you know, these things tend to be a little bit bigger. Usually this is pretty good size fan. And you can see, you know, belt driven, all that sort of thing. And so this one is kind of nice because you've got an indicator over here closed. So if we pull the handle all the way over here, that's going to close the guide vane. We push it all the way over here, that's going to open the guide vanes. So that's not so bad. So it's an inlet guide vanes, 45% open, locked down, 200 horse motor. Now we can just check the curves on this. So we're saying 45%, and let's see, where's my percent flow? I'm getting about 58% flow at 45% open. So let's run back. And so 45% up here, about 58%. So it looks like that curve's working reasonably well if you believe the curve. Okay, so, you know, it's basically the same analysis. So we'd say we're seeing almost $30,000 in savings on this guy, $35,000 VFD cost. I put 2,000 in for the shift change. It's a little bit bigger. So, you know, VFD, about 1.2 years, less than 0.1 years if it's a shift change. Okay, there's another one. I think I'm going to skip through that. This is a nice actuator. You get a pretty good read. That's about 30% open. So this is, if you come across these, you're real happy because it gives you a much better feeling that you know what the damper position is. This was pretty big fan, 300 horsepower. Savings of about 58,000, paybacks less than a year, less than about 0.04 years, pretty quick. This is my favorite. You don't see creative welders like this all of the time, but somebody went to some effort to make sure that the guys out in the field knew that based on the actuator position here, what was open and what was shut. So I wish I got this all the time, but unfortunately you don't. So I didn't run that one. Okay, just to pound home a little more here, some of this may be a little redundant, but let's say that we got a system operating at N1, and this is what commonly happens. This is a common speed reduction project. This is like the shiv reduction. And so this is my design curve. So this is my damper wide open curve. So when we turn this thing on for the first time with the damper wide open, we got flow Q1. We measured it. We said, too much. We closed the damper up here to position B, ride up the fan curve, put more resistance in the system. So we operate here, which is our desired flow, but we've driven our pressure up. Whereas if we open the damper and slow this thing down, we can operate at C. And so, my goodness, we can save all this pressure from P3 up to P2 is wasted pressure because of the damper operation. So we slow down to N2, we open the damper and we operate here and we save energy. This is a 75 horsepower combustion air fan. This works on boilers quite well. This was actually in Brazil on a trip a while back. But what was nice about this is they had actually taken the data before and after. And so this is the measured data. These are the inlet guide vanes. One way that you can see them out here on the fan, get a close up of them. And then of course, you know, the actuator changes the position of all these things in unison. This was the actual measured performance data. So we see typical curves, inlet guide vane curve and the variable speed curve as measured versus airflow. The DCS, the system, allowed us to go back and divide the operating time, operate 8,400. And so we could divide it into bins, different airflows, which is, this is really nice. If, you know, if you're going to modulate flow, it's nice to have this kind of load duration curve. And then you can calculate the demand and the energy with damper control and the demand and energy with VFD control. So this wound up to, this was 8 cents a kilowatt hour power, savings about 9,500, 15,000, so about a 1.6 year payback. And that, like I said, that's measured information. Another boiler, this was with discharge outlet damper control versus boiler capacity. And so you can see the VFD versus the outlet damper control. So I'll move on from that. Okay, so these are captured from New York Blower Company newsletter. So this shows, again, the damper position, the damper control. We've kind of been over this a little bit. This would be the system resistance with the damper wide open. So this would be our fan selection point. We're going to close the damper, operate up here. This is damper position 90, 60, 30, and 0. So this looks like this is 75% on the damper, which would get us to this point. This is the damper resistance, which is the waste in the system, and we see the brake horsepower curve. But that's what happens if you do damper control. This is pretty nice. This is why I put these in here. This shows what happens with the inlet guide vanes. So the inlet guide vanes actually recast the fan curve at every different degree opening position. So we draw 3 of them here. So wide open 90 degrees, this is our fan curve. So this is our system curve. And we don't have any dampers or anything, so the system curve is not going to change. So this would be our fan selection point. And this brake horsepower curve goes with a 90-degree damper position. We get a different brake horsepower curve for every damper position. So we look at 60. If we were to close them to 60, then this becomes my fan curve, and this becomes my power curve right here. Yeah. And so if I go from 90 degrees wide open to 60, I'm going to drop here. So notice I'm just writing my system curve down, and I'm readjusting my fan curve. So that's kind of what the variable, that's what the speed control does as well. It's just the speed control does it a little bit better than the inlet guide vanes. And then at 30 degrees, this would be my fan curve, and I'd be operating way down here. And you see my power curve is now way down here. So you see, oh my goodness, if I had to get to this same operating point with the dampers wide open with the discharge damper, I'd have to be operating way up here. And look at all of the waste that would entail. So the inlet guide vanes are not bad at all. I'm not really criticizing them. Here's a quick example as we're going to go from the 3 different types of control. This was on a pretty big system. This is at design, 150,000 CFM. Brake horsepower at design was 1257. We were throttled back to 110,000 CFM, and the brake horsepower went back a little bit to 1095. And you can see the design static pressure was 40 inch, and it goes up a little bit. Looks like, I don't know, 45, 44, 45. And that's the damper resistance there. You could have, you know, opposed blade or parallel dampers, whichever. Here's the operating cost for 350 days a year at 5 cent power, about what, $343,000. If we go to some kind of inlet guide vane or engineered box, which imparts that pre-swirl, we can change. And now we can operate down here on our inlet guide vane curve. And we can see that my brake horsepower is going to fall to 880. And my operating cost is going to fall to 275, about 276,000. So that's a pretty nice savings just going to inlet guide vanes, which are not that expensive to implement, by the by. And this is going to be an expensive drive, right? I mean, we're talking, this is probably a 1,500 horsepower motor. So there's going to be some cost associated with that. Now, I can say this, and I meant to open the file and I didn't, but about a year and a half ago, I was at a big ADM plant in Clinton, Iowa, and they had a big cogen facility there. And they had 4,000 horsepower fan, 1,500 horsepower fan, and another like 2,000 horsepower fan. And we were looking at putting VFDs on all of these. And we got a quote from, I'm not sure if it was ABB or Rockwell, one of the big drive suppliers. And for all 3 of those, which, you know, was a pretty significant purchase, just the purchase price on the drives came in at $135 a horsepower, which was pretty darn good. I mean, I've seen estimates at 200, 250. So these medium voltage drives are coming down in price. Now, installation, because I mean, I think they need to have HVAC refrigeration. They need to have some air conditioning in the MCC, which you may not have or may not have enough. They require a good bit of space, which can be a problem. So if it's not designed in on the front end, you may have some issues with getting a VFD in there. At any rate, okay, now we're going to go to speed control. And it's a similar picture. We just have a different fan curve at reduced speed, which gets us down now to 521 brake horsepower, which reduces the operating cost to about $163,000 a year, which is about $180,000 reduction from where we started out. A little bit on the belt drives. So, I mean, a lot of energy across the country goes to belt drives. So And and I will say there's some studies ongoing right now. ASHRAE is doing a big study with AMCA, I think is doing it for them, Air Movement Control Association. They're big players in fans and blower testing and fan testing and all that sort of thing. Big study. I think the report should be due before too long, where they're really looking into all of the different types of belts and drives. There have been some studies in the past. The kind of the general rule of thumb here is that this is your standard V belt, standard sheaves, and for larger, they're, I don't know, 4% loss, 4 or 5% loss, depends on size, amount of torque. The synchronous belt, this is like a cog belt, like these guys. I think this is what Harley Davidson kind of uses on their motorcycles these days. Much better. Okay, so you're talking 1 to 2% loss compared to maybe 4 or 5% loss on a situation like this. This is the old, this has been out there a long time. This comes from AMCA 203. It's kind of the standard old V-belt loss table based on horsepower. You see the kind of the general number goes down to 4%. We get above 100 horsepower, it goes up, and you get this big range. So that's kind of what people, until some of the more recent studies came out, that's what was out there. Notice that you have V-belts, and you can join them and have multiple belts. But there's cogged Vs and standard Vs. And there is reported to be some energy savings going from just a standard V to a cog V. It's not huge, maybe 1.5, 2, up to 3%, but you don't have to change sheaves or anything. You just buy the cog belt, and unless you're transmitting maybe a really huge amount of torque or something, you can check with your belt suppliers. They'll know, but like Gates and some of the big guys, they, just next time you change V belts, you could go to a cog belt and you would reduce your energy a little bit. These are just more flexible, and the belt doesn't eat up quite as much energy as it travels around the sheaves. And of course, the synchronous. Now, on the synchronous or the timing type belts, there's good and bad. They're efficient. Some people report them to be noisy. I've been in plants that had them and said, we can't tell the difference. I've been in other plants and said they wouldn't have them. They had them and they took them out because they were noisy. They also don't have any slip because of those cogs in there. And so if you're starting and stopping a fan or a load significantly, then you're going to jerk the heck out of it. Now, if you got a VFD or a soft start, then you don't have to worry about jerking it. And if it's already a noisy plant, you may not. But I've had other people said that they didn't really notice much of a difference in noise between them. So, I'm not sure. This is some data from an old test result. That's too much to talk over in this forum. Here's an example of a 75 horsepower drive that was converted to synchronous belts from conventional V belts. I got these numbers from somebody. I didn't pull all of this, but anyway, approximate cost of a system with V belts. So we're looking at 2 sheaves, 102 and 130, 4 V belts, 108, so 340. If we did this same system with synchronous belts, we see the sheaves are, the sprockets, I guess, are more expensive. The belts more expensive. It's about $1,000. Assuming 5% belt slip for V belts, an energy cost of 8 cents. Fan operates continuously. Predicted savings about 2,000. So conversion cost 1,500. So it's in the neighborhood of a 1-year payback or less. So if you're willing to live with the synchronous belts, that's something that you probably should look at. Okay, now I have some software, and this stuff is downloadable for you. There's actually 2 different programs, and we're going to look at these briefly. And I have a little example, and then we're going to conclude my remarks with that. But the old software, and this came out in like 2004, 2005, is FSAT, Fan System Assessment Tool. And if you Google US DOE download FSAT software, I did it just a few minutes ago, and there's still a download link. So I think it's still available. And it's certainly possible to get this one. And there's a newer system out there I'll talk about in just a second. But this is just a pretty sophisticated fan-based calculator that will help you do an analysis. You still have to do the analysis. You have to get out there and figure out what you're going to change on your fan system. But it really simplifies doing the calculations. Both of these tools do. So I'll let you look at those. And these are some other characteristics. This is out of an FSAT workshop I went to a long time. It just helps to quantify, see the big picture. It'll calculate the efficiency of your fan for you based on measurements. You go out in the field and take some data, come in and plug it in, that sort of thing. So we'll see that. So this is our plant that we're going to work from. And this came from the FSAT training. I think Ron Robalewski put this together a long time ago. But it was an OSB plant that they went in and did a detailed fan study on. And so there's multiple fans here. There's a combustion air fan that basically is drawing warm air off of the top of this waste wood boiler or burner situation. Duct system, an orifice plate for measurement, went through a fan, and then it had a discharge damper that was heavily throttled. So that was really the condition that turned them on to this one. And this is the fan we're going to run through some numbers on in just a minute. But anyway, so it's blowing hot air through the drum dryer. And then of course we've got particulates and stuff we gotta clean up before we get rid of the air. So we go to a primary cyclone, secondary cyclone. We've got an ID, a dryer ID fan, blows into a spray chamber. We've got another damper. We got an E-tube scrubber, and we got another fan, and then we go to a separator and then up the stack. So that's the P and ID diagram. Here's the product flow diagram. So they brought in logs, they chipped them, they dried them. The air went through a cyclone. It all went to a cyclone, and then the chips fall out to a mixer. They put resin with it. They press it into board, and they saw it, and then they sell the boards. So that's kind of what the plant's doing. Now, this was the overall success of their project. There's 2 combustion air fans, and KW went from 144 down to 44. That's pretty good. 2 dryer ID fans went from 332 down to 154 kW, and 2 E-tube ID fans from 202 to 146. So across the board, they had about 338 kW of reduction based on their fan study. Okay, so here's what we're going to simulate in these software tools. So I've got, they've got 2 of these combustion blowers, and this is just looking at one of them. They're both considered identical. So this was times 2. CFM measured at 8,080. Pressure developed by the fan, 42.7 inches. Pressure required by the process, 12 inches. So pressure drop across poured ductwork was measured at 2. So they redid the ductwork. Pressure drop across the damper, they took out the damper. And pressure drop across the orifice plate, they took out the orifice plate. And so we went from 125 horse to a 40 horse. So I think they replaced the fan. Brake horsepower, and so power draw from 72 to 22, and the annual energy cost was 28,800, and they reduced it by after to 8,800. So they basically saved $20,000 with this. Okay, so now I'm going to break out of this. Well, now let me see. I got 2 more slides here. I need to. There we go. Okay, so this is the FSAT screen. This is a screen capture. I've got it live here in just a second. We can go to it, but I think this might be easier for you guys to see. So this, all of the inputs are over here. So you've got a bunch of different fans modeled, different styles and all that sort of thing. And usually you put in the rotational speed of the fan. You can put in a wheel diameter if you want to by this pull down, but so we'll put in a fan rotational speed. And changeable, this has to do with this optimization rating. If you say changeable, you will let it look at any type fan in order to figure out the maximum possible efficiency. So that may or may not be practical. Most times, even if you're going to change a fan, you probably would stay with the same fan type, but that's up to the operator of the program. You indicate a motor efficiency class, energy efficient, standard, whatever. A voltage, a nominal motor voltage, probably 460, unless it's, medium voltage. Operating parameters, this is 8,000 divided by 8760, the fraction of the year. And this is the electrical cost. Let me tie down my marker here. I shouldn't have gotten out of this. Okay. 5-cent electricity is what we're simulating here. This is field data. So you went out in the field and you measured the power going into the motor at 72 kW. We left the voltage at 460. This is the measured flow rate. This is the fan pressure increase. Static pressure was 42.7 was the increase across the fan. Gas density, if you don't know, you can estimate it. This software has ability to estimate air densities. You just click this and go in the background and give it some information. It'll give you a density and also give you a compressibility factor. Okay. So the output was that this analysis showed the fan was operating at 59.9% efficient, 125 horse. That's what I input to it. Shaft power was 92, motor efficiency 95.3. And see, this is the FSAT has the ability to come up with these efficiencies based on background information it has built into it, which is nice. It can also has power factors it can pull. So it'll calculate the motor amps. There's the electric power. I input that, so it just repeated that. Annual energy in megawatt hours. And there's our $28,800 in cost. Okay. Optimization rating, if you're going to replace the fan, you might pay attention to that. It can see, if I allow it to change fan types, it could see doing this at this pressure. It could see doing that for 21,400, but I'm going to change the system. So here is the after case where everything is pretty much the same, except we've changed the measured fan static to 12%. And he had a measured power in the, from his study of 22. So we say it's going to fall to 22. So my fan efficiency is going to change a little bit to 57.7. But there's my $8,800 a year operating cost. So then my savings are bearing out here. It's the 28.8 minus the 880. Okay. So how am I doing? Okay. So let's see what I want to do. I want to get out of this. And so this is FSAT live. Now I can change whatever I want to. So like on fan configuration, if I go to, it says changeable. If I go to fixed, it's going to stay with that same type fan. Let's say I got to turn it back on. There we go. It wasn't running. Okay. And so this was 81 before. And now if I stay with this same fan type at that situation, it can see about 75% for an optimal fan motor efficiency. So, but basically, this is just a sophisticated calculator sheet that you can use. And so if I want to minimize this, I have to stop it and put it down. Now, the current tool that DOE is putting out and promoting is Measure. And Measure stands for manufacturing energy assessment software for utility reduction. Okay, and so if you, yeah, and this is downloadable. It's if you just search on Measure download USDOE, you'll find it. And Measure has lots of capabilities. It's not just a fan tool. It has a pump assessment. It has process heating assessment. There's the fan assessment. It can do steam system assessment. And it has a tool here to facilitate and do calculations based on an energy treasure hunt, which we don't have time to go through all of this stuff right now. And we also have calculators over here that will do various calculators for you. For example, we're doing fans today. If I click on that, I have a fan traverse analysis. So if you've gone out and taken with your pitot tube and taken your pitot tube traverse, you can click on this, put in your data points, and it will calculate the power, flow rate, pressure, etc. for you. You can calculate a fan curve if you have measured operating points, or you can calculate the achievable efficiency based on different types of fans. So that's what they have in there under fans. And they've got lots of stuff on motors. And like I said, we don't have time to go through all of this. Motor drive, if you want to check VFDs, or different belt options, you have some energy savings projections possible here. Replace versus rewind, efficiency, all kinds of stuff. Okay. So let's see here. I went ahead and did. So this is the fan OSB combustion fan. So I did this previously. So let me pull that up for you. And let me see. Because this header is in the way, I'm going to make this a little bit smaller so that I might be able to get to all the buttons without screwing up Zoom. We'll just do it like this. I think this will work. That's pretty good. And when you fire this up, you get all these disclaimers, and they tell you if you find an error, let them know. So, you know, this stuff has not been out there all that long. But when you start an analysis, you start with system setup, and you go through all of these tabs. And so the first tab, assessment settings, you basically are just selecting units. What system of units do you want to work in? Inches of water, or you can go imperial, metric, or custom. You can just select whatever you want. For the fluid, you can select air. I don't know what all they have in here. Other gases, you know. And then you have to give it a density, or you can give it some other characteristic that it can calculate a density from. So you put that in. Here's your fan type. It's got bunches of different fan types built into it, just like FSAT. I mean, this thing basically is mimicking back FSAT, but it's new, and this is going to be maintained and improved over time. So you're probably better to learn this one than just the FSAT. The fan speed, the type drive. So we're telling it right now we've got a V belt. It does have all these types of belts in here. Then the motor. So it's doing the same thing that FSAT did. You just have to go through all of these different pages to kind of get all the information in. So, you know, until you get used to it, you can get a little bit lost in here, but if you click around long enough, you can find all the stuff. Frequency, rated power 125, motor RPM, energy efficient class, etc. Full load amps, if you don't know, you can click on this and it'll estimate them for you, which I think is probably what I did to get that. And then the field data. So this is, instead of putting in the fraction of the year, you can put in the 8,000 hours. Electrical cost, 5 cents. Inlet pressure, I wanted the 42.7 developed across the fan, so I put in 0 and 42.7. You know, I mean, really, this is going to be a negative number, and this is going to be a positive number, and they're going to combine to get 42.7, but for the analysis, it doesn't really matter. 8080 was the CFM. Load estimation was power. If you had current measurements or estimates you could put in. There's my 72 kW, 460 volts, and this thing puts a specific heat ratio, CP over CV, and it shows you a compressibility factor that it has calculated. And so then this is the result of my baseline, and I see my annual cost is $28,800. Well, that's good because that's what I wanted it to be. You can look at a report at, well, let's go through the assessment stuff because I went ahead and did the modification. So if you want to do the modification, then you click on assessment, and it has two different views. It has the novice view and the expert view. So we're all experts, so we'll just go to that. You can punch around on both of them. And you see that I've already put some stuff in here. So you can view existing or add new scenarios. So see here, I had the eliminate damper and losses. So I'll just click on that and then it brings it up. And so then what you do is you can go through each one of these tabs. And so this would be your base case and this would be your modification that you want to run. And so, you know, I'm not changing fluid or density or anything like that. So I didn't change anything there. I'm not changing the fan. And, you know, the fan efficiencies, whatever it calculated it to be. I'm not going to change the drive or anything. So I haven't changed anything on that. On the motor, I'm not changing anything on the motor at this point. Now, I mean, I could if I had selected a new fan and I knew what it was going to be, I could. Or I guess in the previous slides, he's going to put a 40 horse on there. I guess I could have put a 40 horse on there, but I didn't. So here's my field data, and this is what is going to change. I'm going to change this 42.7 static developed to 12 because that was the basic change that he made. And you see it does change compressibility factor a little bit, but let's see, I guess, do I need to run? No, okay. So it shows me right over here, and I can get a report on this, but it's showing me my initial cost was 28.8 and my modified cost was 8,809. So I picked up $9 different from the previous analysis, but you know, that's pretty close. And so then I can look at a report and it shows me all that information. So I get a percent power savings of 69% for changing that fan out, which is pretty good. And this just gives the calculated numbers before and I don't know, rated horsepower. Oh yeah, I didn't change motors yet and that sort of thing. So I could go back and change motor and it would probably project a little bit of additional savings. Let's see. So now I've run one other thing. So let's go back to the assessment. And let's see, view, add scenarios. I went ahead and I said, well, shoot, what if I talked about changing to a notch V. And so this is the same, let's see, field data. This is the initial scenario, the 42.7 inches of static. And all I did was change the, where was that? I guess it was on the fan. Yeah, from a V belt to a notch V belt. I wanted to see what it would project that savings to be. And so it sees that savings as $334 a year. That's probably not a bad number, 1.9%. That's probably a pretty reasonable number. Now, if you replace the fan and ran this with it, then you're not going to see that 334 because it's not transmitting as much power, once you do the fan change out as well. Okay. Let's see. So I think that's pretty much does the measure demo for you. I mean, I've got lots of different stuff. I've used this thing for a little while, but I like it. Sometimes, you know, for screen captures and putting stuff into a PowerPoint, I kind of like the old FSAT because I can get it all pretty much on one screen capture. To use measure, you've got to somehow capture all those different screens. So that's a little bit awkward. Let's see here. Okay, there's some, you know, for energy fan optimization. There's some stuff in here about, you know, from the corporate financial product prediction, you may improve product quality. You're probably going to reduce maintenance, that sort of thing. Additional maintenance safety, certainly quieter, because if you wind up slowing these fans down, a lot of times fan noise is significant. And so that can be a big benefit. Again, things not wearing out as fast, dampers pinched, that sort of thing. And, you know, reduce energy, save the planet, all that sort of thing. So I think that pretty much ends my presentation. So let's see, I think Tim, you wanted me to stop the recording. Well, let's ask if there's any questions. So anybody that has any questions, please jump on, unmute yourself and please ask. No?
Yes, sir. Hey, my name's Dennis Gates with Steel Dynamics, Columbus. On density, temperature of the air, so it affects the power consumption, and does it also affect the CFM?
Not the CFM. Let me go back to those slides here real quick. That's a great question. Love it. Let's see. I'm lost in my own slides. I think it's right here. Well, let's go this one. This is probably, I'll just leave it there. Okay, so you see Q is CFM, no change. A fan is a constant volume device, but you got to realize when you change temperature, you're changing the density of the air. And so if the air gets more dense, you're blowing more molecules. You're moving more mass. And so if you get more dense, if you're moving more mass, it's going to take more power. And if you're moving more mass in that same ductwork and fan, you're going to build more pressure. Okay, so pressure changes and power changes, but flow rate doesn't change. And these were the curves. You know, this was pretty extreme. I hope you don't go from 70 degrees to 600 degrees. That would not be good if you blew that on somebody. But anyway, just kind of just makes the point. At 70 degrees, this is my fan curve. And these are the pressures I'm getting. I'm getting, you know, like 40 inches. And at half the density, I'm down here, I'm getting, you know, in the 20s. And so that fan curve is going to change in direct relationship to that density ratio, and the power curve is going to change.
Okay, appreciate that.
Yes, sir. Thank you for the question.
Yes, sir. On VFD drives, I got a question. If we're running 60 hertz, then we're actually consuming more power than we're on across the line. So you can figure the VFD loses 4%.
I didn't quite catch the last of that. If you're running a drive at 60 hertz, you're shooting yourself in the foot.
That's what I'm saying. We're actually using more power using VFD.
Absolutely. You're doing a couple of things. One, we've been taking some oscilloscope measurements upstream of the drive. And now I've got a 15 horsepower fan and an ABB, about a 6 or 7 year old drive. But there's significant noise, electrical noise, gets transmitted back onto your circuits by that drive. Now, if you got a new drive, it's probably better. But so one, you're costing yourself 2-3% in additional energy, and you're putting additional electrical noise, harmonics out on your power system. So, and both of those things, they may not, the harmonics may not be causing you any problems, but you know, sometimes computer-based control systems can be adversely affected by that. So there's two good reasons to not do that. I'd take that drive, you know, if you can't turn it down, then take it off, take it to another motor that you can, you know, modulate, that you can slow down.
Okay.
Sir, I guess the question would become, what are you using the drive for? If you're using it to start the fan,
Well, that's a good point. If you're using it as a soft starter, but you know, you're going to pay that, you know, unless you can electrically, once you get it started, get the drive out of the circuit. I'm not electrical engineer enough to know if you can do that or not. But if you're running all the power through that thing, you're going to have that 2, 3, 4% drive loss. But yeah, soft start, that's a good point. That's a good point.
and not even a soft start, right? Soft starts won't start everything that a drive can. So you have to be real careful between all three fan starting methods.
Okay.
So soft starts are limited. Drives can start the biggest loads typically. Direct online, you're limited by your motor and your distribution system. So
Right. Agreed. Very good. Thanks for those comments. Yeah, the energy guys, we sometimes lose overall perspective. You got to be careful when you're dealing with just an energy guy. You got to make sure you look at the whole picture. I agree.
And as far as your drive noise is concerned, you should always be putting some type of line filtering on that drive. So at a minimum, line reactors, you know, if it's an extremely noisy drive, you might even need an isolation transformer.
We run line reactors on. It's just that our system's changed over the years when we first put these drives in. Now the demand is new. So growth has driven us to run with 60 hertz.
That's great. Good discussion. Anybody else? Jump in.
Pictures, I believe it was a discharge damper on a 125 horsepower fan, if I recall.
Yep.
And you know, you had showed the power cost savings of installing a drive because the discharge damper was in a fixed position that wasn't 100% open. When you did that project, then do you take the damper completely out of the equation, completely remove it, or do you just put it in a 100% open position and allow the VFD to do its thing?
Well, that's a really good question. So, I mean, what I would say is the options. One, VFDs do go down. If the VFD goes down and you have to bypass it, you're going to go back to 100% flow. And if you want to operate, you may need to have that damper there. Now, that damper is going to have a pressure drop. Even in the open position, it's got a pressure drop. So right. I would say it depends on how critical that fan is. You know, if that VFD went down for a short period of time, how big of a problem is that for you? Because, and the other thing you could do is you could measure the pressure drop across the damper, or, you know, talk to the damper people, see what they would estimate it to be at your flow rate, and then use that simple little equation, or you could do it in one of the calculator tools and see how much that pressure drop, having that out of there, would save you a year. I mean, if it's a trivial amount of money, I would leave it in. If it turned out to be, you know, a fairly significant amount of money, then I would evaluate. Or if it's a critical fan, then I would leave it in and just lock it open.
Okay, thanks.
Because again, the energy guy can get you in trouble. Oh yeah, take it out, you'll save more energy. And then the drive has an issue. And all of a sudden you're down for 3 days and nobody's happy about that. Anybody else? Great discussion.
One thing I had a question about, you said checking your Pitot tube moving in different areas, rectangular round duct, sure that'd be great. Get an average, but in a perfect world, that don't happen. So is there any particular location around or square duct that, position wise, it's more accurate than trying to, measure quadrants or different layers in there?
Okay, I had a little trouble understanding, but was that in terms of taking flow measurements?
Right.
Okay. Well, the rectangular or round doesn't matter. What you want is a good long straight section of duct, if you can find it, so that the velocity profile has become as uniform as you can get it. And so you don't want to, say right after an elbow or right before an elbow or something like that. I mean, if you had like and there's a recommended number of diameters upstream. What is it? 8 to 10 diameters upstream and 4 or 5 diameters downstream of straight duct, something like that. But I would, the longest straight run you can find and get kind of in the middle of it. You want more upstream than downstream. Will smooth out that velocity profile and make your measurements better.
Yeah, that's what I was kind of figured. Put it in the center, basically. And like I say, try to find the longest straight run you can do. So.
Yeah, and you do need to do a traverse. I mean, if you just want relative numbers, you can just measure center line. If it's a turbulent velocity profile, it's going to tend to be fairly flat until you get over close to the walls. But I've used a Pitot tube some, and and it's a challenge. I mean, it really is. You gotta get you a good location, and you got to do your best to get that thing, directly pointing straight into the flows and this, that, and the other. So, and try to get your positions correct. So taking good Pitot tube measurements is not easy. It takes some work and planning.
Do the fan laws always apply to centrifugal type fans and things, or is there ever a fan type that the fan laws don't work well with?
Not that I know of. That's a good question. No, I don't, not that I know of. I've never really thought about any condition that, any type of fan that they wouldn't work with. I know certainly centrifugal. I think actually on centrifugal fans they're good with. So whether there's something else out there that would not apply, I'm not sure. I mean, you can't use them with an air compressor or something like that. If you go up beyond the realm of, being a fan per se, to too high of pressures. But what, fans go up to what, I don't know, 3-4 PSI, something like that. I mean, you can get up pretty high with some fans. So not that I know of is my answer. All right, Tim, looks like we're done on questions. You want me to cut off the record?
Yes, sir. Please go ahead and end the recording. We'll have a link to the video.